Welcome to the classes of GPU architectures and programming. In the last lecture, we have been discussing about how an operation like matrix multiplication can be accelerated with proper optimizations involving the shared memory. And in this lecture, we will continue with some more examples, maybe a bit more involved, and we will also try to show that how you can be able to perform some monitoring based on the optimizations and figure out how well the optimizations are working for you using some profiling primitives that NVIDIA provides for you. So, for as an example, in the last case we considered the operation of matrix multiplication. In this case, we will consider this example of matrix transpose. So, if you remember from your high school algebra, matrix transpose was a simple operation such that suppose you consider a matrix A is given to you and you want to create a transpose. So, the way you would be defining the entries of A transpose would be that whatever was an entry of the ith row jth column Aij in the original matrix, in the transpose matrix they should be the entry in it should be the same entry in the jth row and ith column. So, the way it is going to work is that in the transpose matrix, if you consider any entity in the ijth column, it should be same as the entity in the jith column of the original matrix, right. So, this is how it would hold at the element level, that in the so essentially if we take an example as has been provided here. So, as you can see that we are considering an original matrix which is like this, the one that is given on the top left, and when I do a transpose, essentially all the ijth elements in the original matrix become the jith element in the transpose matrix, right. So, essentially I can just say that the diagonal is remaining the same and the rest of the elements are just flipping over to the other side. So, this comes here, this goes here, and similarly for all the other entities here. But how is it going to really happen in the underlying architecture? That is the important question here, right. So, if I look at the arrangement of this matrix with respect to the memory, then for all practical purposes this is in derivative of C. So, we have a row measure implementation, right. So, your matrix is finally resident in the GPU memory in a simple consecutive locations for the different elements in the row, followed by the next row, followed by the next row, so on and so forth, right. So, when you are really doing a transpose operation, things as you can see that which looks very nice in the original 2D representation, you may lose that simple property here. Of course, in terms of the matrices is fine, but here things will be happening in this single one dimensional array, which you will be accessing using the row and column indices of the original matrix, that actually you have to again compute using the block and thread indexes of the original matrix. So, if we just consider a simple vanilla matrix transpose function in C as a CPU only function. So, how really are you going to go about it? You will just write a cascade of loops, right. One loop is iterating over the rows using whys, right. So, the outer loop is iterating over the rows. So, this IY index is iterating over the rows, and the inner loop is iterating over the columns per row, and inside what you are doing is you have been given a pointer pointing to the input matrix, and you are going to write the data into the output matrix using this out pointer. So, essentially you are just you are just copying elements from the y xth location to the x yth location, right. So, I can just say that this is in terms of the representation of this code, whatever is in the y xth location, the index in y axis and index in x axis gets flipped to index in x comma index in y location, right. So, these are some of the examples taken from this book by professional book on professional CUDA C programming here. Now, if we consider a GPU version of the code, what would happen? Of course, since in the CPU I would have a cascaded loop, and so it is a sequential loop and it is iterating over the 2D arrangement of data points and using the loop iteration variables and doing the transformation from the in matrix to the out matrix, right, by accessing these entities. But when it will be done by the GPU, it will be again the work will be done in a part thread basis. So, you will launch a kernel, I mean as is always done, you will launch a kernel and you will define the part thread activity. So, every thread would need to compute its ix and iy values, that is on which location of the matrix is going to work, right, and then is going to copy the corresponding location from the in matrix to the out matrix. So, the thread, every thread will discover which location it is supposed to work on, and then is going to copy here in the corresponding location where yeah. So, whatever was the row number, it was IY, it changes to the column offset here, and whatever was the column offset is going to change to the row number here, right. But so again we are calling it as a naive implementation because I am not making use of any shared memory or other thing. Of course, we think that it can be optimized further using such implementations, we will get into that. But here observe what is happening. So, essentially I call it a naive row implementation because we are loading by rows and storing by columns. Why do I say that we are loading by rows? Because think how the warps are getting formed. So, you have thread IDs for consecutive locations in the rows. I mean you have a warp which is containing thread IDs 1, 2, 3 like that, and they are accessing in the input matrix, they are accessing consecutive locations, right, and forming a warp, right, and they are loading the data from these consecutive locations, which would mean the loads are coalesced, right. So, whenever this thread inside a single warp, this thread is loading this data point, the next thread is loading the immediate next data point, and like that. So, this is going to get coalesced. But what happens when the threads in the same warp are going to write? So, here whatever for this example that I am trying to draw, the so essentially we are picking up items at the lower level with a large row index, right. So, that large row index would change to a large column index here. So, maybe somewhere from here I would be starting to drop the elements, right, and we are having offsets like this, right. So, this column offset values would be changing to row offset values, right. So, if I say I have a large row index and a small column offset, so that would transfer to a small row index and a large column offset. So, essentially this thread would be storing the data somewhere here, the next thread would be storing somewhere here, and the next thread would be storing somewhere here, like that. No, wait a minute, let me draw this with a bit more accuracy. Sorry. So, consider a fresh picture here. We have the original in and outs. So, this is my in and this is my out. So, let us assume that I am doing again the same example. I am doing loads. I mean, I am accessing the warp is definitely accessing consecutive locations in the row. Why? Because inside a warp, this y value, I mean, since the warps are going to access consecutive locations, and the consecutive locations would mean consecutive locations in the row in general, as long as the warp is the size dimension of the matrix is divisible by the warp size, right. So, look, observe, you consider that you are loading data from these points in a single warp, right. So, these are your loads and they are all coalesced. Now, what happens when these threads are going to write? So, this in index is going to be written like this, right. So, you have a large offset here with respect to y, and then for the same row offset, let us give this some name. Let us say this phenomenon is happening for some value of I y, and let us say the I x values are 1, 2, 3 dot dot dot, right. So, now when you think that where are these coalesced load values, the values which have been loaded by the warp in a coalesced memory access, where are they going to be get stored in the out matrix? Now, that would be interesting. Why? Because now this I x value flips to become the this I y value, which was the row index, flips and becomes the column index, right. So, here let us just consider the first thread here. So, it was loading data from a location with I y comma 1, right. So, that would mean it is now going to download that data at in the out matrix at a location 1 comma I y, right. So, that is it. So, let us say this is the first row. So, the data would be coming here. What about the next one? So, the data was at IY comma 2. So, it should get in 2 comma IY, next 3 comma IY, like that, right. So, essentially whatever you loaded here consecutively are going to get stored in the ith column from the ith row. So, essentially you are doing a load by row and you are storing the data by column. Now, of course, if you think from the access patterns, all these writes are non-coalesced, right. Technically, considering a big matrix, all these writes will require separate global memory transactions, right. So, that is why you will have coalescing. The good thing about the goodness of coalescing will help you with respect to the loads, but since you are storing by columns, you will be having a penalty here. Now, consider the other scenario where so as you can understand that this was a simple GPU kernel where all we did with respect to the original CPU kernel was we removed the two loops and just defined a part thread activity. Part thread activity was that okay, you just load values and put it in the transposed location in the output matrix, but I have two options now as we are discussing here. The first option is you just load by row and store by column, and since this is one option, of course I have the other option that why don't I load by columns and store by rows. It is very simple to think. So, all that will happen is that your access expression is just going to change. So, this is the example where you are going to load the data by column and store the data by row. So, I can just reuse the same picture here maybe. So, since I am loading by column, I can say that this is my in matrix, this is my out matrix, and I am loading these data points from the column, right, and what would be coalesced would be the writes, right. So, I will have memory access coalesced for write by the same verb. So, this is now write and this is now read. So, I have now got separate global memory transactions for each read operation or store operation or load operation, right. So, now I will have the advantage of coalescing while writing, since I am storing by rows, and I lose the advantage of coalescing in terms of reads. So, as we can see that these are the two options I can have, but in both cases either my reads are coalesced or my writes are coalesced. That would give me some parallelization in terms of reducing the global memory loads or stores, but I do not get both. Okay. So, we have explained the idea of this check macro, and let us look at how to write the driver code including this macro. So, essentially we are trying to write a simple driver code here, which is the host program, where we will be using this check macro to nicely capture the device properties of the underlying GPU device and print them up. Next, we set up the input arrays, and we we are trying to write a single program through which the user can input what he wants, as whether he wants to do a transpose by naive row or by naive column, and that would be the user's preference coming through, which would be captured by the main program using the argv parameters. So essentially, I am assuming you are all familiar with handling command line arguments, right? So the ikernel variable is matching its value with whether, I mean, so I am using this a2i function to actually process the argv string, and this argv string is converted from the string type to a2i in integer type, and it's stored in the argv ikernel parameter, and then so that is actually storing the user's preference of what kind of operation he wants. And the next thing we do is we just set up the normal grid and block launch parameters for the kernel. I mean, what is the block dimension, block x, block y definitions, and the grid dimension in terms of the way you want the number of blocks to be parameterized like that. So this is how we are writing that what should be the number of blocks. I mean, so essentially you divide just nx by the block x and ny by the block y, right? So that gives you this 2D system will give you the total number of blocks, and here you have the definition of the thread block. I mean, how the blocks are arranged in terms of block x and block y. The next thing you do is you make suitable allocations for the host memory side. Sure, these core programs will also be available to you, and then you make this call assuming that there is a function which is going to allocate the host array, right? This host array HA with the input with all the input values stored, and the dimensions are of course nx cross ny for this array, and then you allocate device memory in DA and DC. So you want the host array to be transferred to the device memory using this CUDA memcopy command. So in device you are defining two memory locations, DA and DC. In DA you are copying the host array, right, using the CUDA memcopy command, and everywhere you are using the check macro to check if there is any system error, then the check macro will nicely print the corresponding statements for debugging purpose. And here we use a function pointer to actually parse the user's input choice, because I have already captured the user's input choice using this ikernel integer, right? So argv1 is containing the first command, the first option provided is containing what is the functionality that the user wants to execute, right? So then here through a switch case we are trying to match this this value of ikernel, whether it's a 0 or 1, and accordingly depending on what is the user's parameter, we are trying to set this function pointer kernel and provide it with the pointer for the device function transpose naive row or transpose naive column, right? So essentially we are using this, we are setting this function pointer up here through this switch structure, and the user has already passed what's his preference in terms of the in terms of this argv parameter which has been passed to ikernel, right? So coming here, we are finally running the kernel. So as you can see that now this function pointer kernel has been suitably initialized. It has been provided with the address of either transpose naive row or the transpose naive column function, whichever you want, and then this kernel will execute, and of course these are all asynchronous statements here, like the kernel will be launched and the CPU will be waiting for the last error message if there is any, and then once this CUDA memcopy command will again be executed to get back the value from the GPU of the transpose, get back the transposed kernel value from the GPU side, right? Now in this example we will demonstrate usage of a profiler from NVIDIA, like how to do a command line profiling using this nvprof tool, and how to figure out what is the performance of your program. So with this initial idea that we can do performance of a programming using this kind of nvprof profiler, we will end this lecture, and in the next lecture we will go into further details of using nvprof for doing CUDA kernel profiling. Thank you.